So everyone, please be aware the meeting is being recorded now. I will put the recording up and send a link to all the registrants tomorrow. And at this time, I'd like to turn the meeting over to our speaker this evening, Zhong Chen.
Thank you, Scott.
Yeah. Please mute your microphones at this time.
Except for you, okay, Scott?
Yes, we can.
Okay. All right, thank you, guys. Thank you, Scott, and thank you, EMC Michigan chapter, for inviting me to give this talk. And Candace, especially, she was doing all the behind-the-scenes work and trying to get me signed up and time arrange the presentations and all that. So this evening, I'd like, or whatever, wherever you are, I'd like to, your time zone may be very different from evening here. I'm going to talk about optimizing EMC and RF test chamber design performances. So when I was given this topic to talk about, I thought this would be a pretty niche kind of topic because, you know, there's not a whole lot of EMC chamber designers and absorber designers in the world. But it turns out we got really, I did this presentation once before, really good responses. And also from, you know, the sign up today, it looks like this is a topic that people do have a pretty good interest in. So I was trying to, let's see if I can advance the slides. So I was trying to think of what why you might find this presentation interesting, and also kind of give you an idea of what I will be talking about today. So I think if you can find yourself in one of these categories, you will find this beneficial today to maybe you will get something out of this presentation. So first of all, if you're involved in procuring a new EMC chamber or need to refurbish an existing one, you'd like to know how the chambers work and what are the things that can get you. And if you're a user of a chamber that has a marginal performance currently, you struggle to meet the site requirements, you might want to learn how you can change, you can modify some things in the chamber. Maybe you can get the chamber into a better performance. Or you just the EMC compliance engineer, or you have a product you need test, and you want to understand how a chamber can impact the measurement uncertainties. So hopefully this talk can give you some behind the scenes and the things we look at when we design a chamber, how these things can impact measurement uncertainties. Or you might wonder why, you know, if my chamber currently, you have a pretty good chamber, but you might wonder if my chamber is the best it can be, what can I do to make it even better? Or the other category, maybe you're just intellectually curious about chamber design and modeling technologies and what we do in terms of, you know, how we go into when we have a challenge in terms of design requirements, how we go about thinking the design process. So a lot of times it's really about, you know, like anything else, when you design a chamber or anything, it's about trade-offs. You know, you can spend a gazillion amount of money, you can get the best performance, but that's not what you have. You have to trade off between monies and features and available spaces and what you can do with the resources you have. So when I talk about optimizations, what am I talking about? So these are kind of the scenarios you might go through when you think about chamber. Most of the times, actually, you need to tightly fit into available building space. We all know that, you know, the larger the chamber you're going to be able to build, probably the better the performance is going to be. But in real life, that you don't have unlimited space and unlimited budget, and most of the time, building space is #1 constraints for people. You know, typically you need to put a chamber into a existing building. And you have, especially the ceiling height is one of the bigger constraints. Or you have budget constraints, you need to trade off between the quiet zone size and maybe absorber linings. You don't want to put absorbers everywhere in the chamber. Can I just partially line the chambers to give me either for budget constraints, or you want a bigger space, you can test bigger equipment. So you might also want to put access doors in certain areas that may be not the best for EMC, electromagnetics and RF designs. For example, you might have to put an access door right next to a specular reflection region where you know this is going to cause some issues in the chamber, and how we can predict these kind of performance and do what if scenario studies. Or you might want to optimize antenna locations within the chamber. So if you are experienced with EMC testing, you know sometimes when you go into a chamber, you do especially normalized side attenuation measurements. When you place the antenna in certain places, you can get a better performance, and if, you know, the different axes and all that. So these are the considerations that you might want to go into, have a better idea before you start testing and wasting your time. And then when we design a chamber, we might be able to take advantage of some of these considerations. Or you might want to need use shorter absorbers in certain areas to maximize the test area. So I kind of mentioned this earlier. You know, we know bigger absorbers typically would perform better at low frequencies. And so people tend to, you know, the safest thing to do is always to use large absorbers in the EMC chamber. But, you know, that constraints, you might not want to do that because of various considerations and test zone requirements. And sometimes this is also a test case I will show later, because I want to show a couple of real world design applications and examples. And one of the examples I show, it actually has two test ranges that we call dual range chamber. So basically you have two receive antennas for EMC tests that can simultaneously operate. So this gives a better throughput. So when you do these kind of things, what kind of impact it can have on your chamber performance. So the point of all this is before you're committing to a large investment, especially your anechoic chamber, or you even invest time into a chamber, you want to know beforehand how these different things can play with each other instead of afterwards. So especially if you go design a chamber, you build a chamber, if it didn't meet all your requirements, that would be a very expensive exercise. So just a little background information about EMC chamber testing. So below 1 gigahertz, a lot of you guys probably familiar with this, but I like to kind of bring everybody up into the same talking level so we know what I'm talking about. So I like to define a few things. So below 1 gigahertz, the figure of merit for EMC, commercial EMC semi-anechoic chamber is the side attenuation deviation, the delta NSA, normalized side attenuation deviation. So basically, this is the height scan antenna response between a pair of antennas. You measure the same pair of antenna in a chamber, and you put one antenna at fixed height, and you scan the other antenna typically from 1 to 4 meters in height. You grab the maximum response against frequency between the two antennas, and then you measure this versus the you measured. You guys still seeing my screen? Scott, you still seeing my screen?
We see it.
Okay.
Yes.
All right.
Yes, we are.
Disruption.
Yeah, sorry, we're muted here.
Yeah. So you measure the same pair of antennas in the chamber in that test configuration, and then you take the same antenna into a measure on the ideal site, and the difference between the two would be your delta NSA. So basically, it's how much between the pair of antennas, the response between what's in the chamber and what on the ideal site. So for below 1 gigahertz, the chamber is semi-anechoic, so the measurement environment is with a ground plane. So your ideal case is the half space problem. So your antenna is situated above a PEC perfectly flat, perfectly infinitely large ground plane. So that's what you're comparing your chamber to that. So we want that difference to be less than plus minus 4 dB. If you're within that 4 dB, you will meet the standards to be qualified for EMC testing. Above 1 gigahertz is a little different. Now the chamber is supposedly a fully anechoic environment, meaning the ground plane can't be conductive anymore. So what people typically do is they move the absorbers into the chamber to convert the chamber into a fully lined room. So now you're comparing the perfect performance of the chamber is a free space environment. For chamber design and chamber performance prediction, this is really the essential part of optimizing the chamber design. So in the good old days, a lot of hand waving involved in chamber design. But now we're a lot more sophisticated. We can actually do a very good job of predicting the chamber performance using the computer tools that we can, look at these different parameters, including the chamber size, shape, absorber selection, layout, etc. So this is kind of the essence of this talk. Is I want to go into a little bit of detail about what we do in the chamber prediction and what is the technology behind the chamber simulation and how we do things and how we optimize the chamber. So of course, all that accurate modeling is really the key component of this. So traditionally, ray tracing using geometric optics to predict the chamber performance is really the dominant method for many, many years, because this is a fast method. When we're dealing with anechoic chamber modelings, it's a really large, electrically large environment. It's very expensive, computationally expensive, or even the computer resources, even a few years ago, even today, I mean, when you're trying to model a chamber in the full wave environment, it's just simply too expensive in terms of computer resources. So geometric optics is basically a ray tracing technique that people use over the years with various degrees of successes. But the problem really with the ray tracing is a high frequency asymptotic technique that works very well at high frequency. As you go lower and lower frequency, the near field stuff start dominate, and these this method, especially at below 100 megahertz, kind of break down. And unfortunately, this is the frequency that's really critical in chamber design. So I'll talk about this a little later. So of course, the opposite of ray tracing is full wave simulation. That means you're really doing a full numerical simulation, either using a finite element method, finite difference time domain, or moment method, and to do these chamber simulations very rigorously. And that's just, even today, it's not very practical. In our facility, we have a 1 terabyte computer we purchased a couple of years ago, and even that, to simulate a low frequency in a chamber, it takes weeks to simulate a chamber. A lot of number crunchings. So in terms of optimization, it's not very practical to use. And of course, the hybrid method is kind of a marriage between the ray tracing and full wave, is what I want to propose and talk about today. It kind of take advantage of the ray tracing speed, and also takes advantage of some of the full wave numerical simulations accuracy. So this is what I will be talking about and how we do simulations today in terms of chamber. So this is a typical setup in the EMC chamber. Most of you guys probably have seen this picture thousands of times in what a chamber look like. Just want to point out a few things, just kind of set up later on when I present the data, people understand what I'm talking about. So you have this turntable in the near side of the picture, and that's your quiet zone. That's where you set your EUT up. And this is on this side, I call the antennas placed on this side transmit antenna. Of course, because of reciprocity, it doesn't really matter when we talk about antenna responses. But for convenience, I call this side transmit antenna side. And then the other antenna is on the far end. You actually see two towers. So this is actually one of the examples of a dual range antenna. So you have two towers can actually do EMC measurements simultaneously, either with two different frequency band or two different polarizations. You can increase your throughput. So the one I'm looking at right now is the one on the right in this picture here. And this is the antenna that goes up and down 1 to 4 meters in height. And when we talk about commercial EMC chambers, we typically say a 3-meter chamber or 10-meter chamber. So then what I'm referring to is actually the test distance between the transmit antenna and the receive antenna. And for NSA testing, for site validation, you would always keep the antenna at the same distance. That means if you place the transmit antenna at different spots on this turntable in the quiet zone, you have to move this antenna on the antenna mast back and forth to make sure you're still staying at 10-meter distance and the two antennas are always facing each other. So that's how you measure the NSA. So you would compare the chamber performance versus the ideal case, which is the half space problem. So the chamber design process goes something like this. So typically when we look at a requirements, when somebody's sending the requirements, I need my chamber to do this and this. And this is how we start. We look at what standards you basically essentially trying to meet. We look at the applicable standards, including C63 and CC63.4. Or some of the newer standards in ANSI C63 requirements or CISPR 16 requirements or some other requirements. So we look at the standards you need to meet and then decide what kind of chamber you need. Either this is a semi-anechoic chamber or a fully aligned chamber, and that we look at what kind of measurement you need to make. You need to qualify the chamber with, delta NSA or free space NSA requirement or side VSWR requirement. And then we look at how big of a quiet zone you need and the test distance. So, typically people choose a 3-meter test distance or 10-meter test distance, depending on kind of the requirement and budget you have. 3-meter is allowed and 10-meter is more accurate. And that's, that's a lot of times people take a compromise and say, I want to do 5 meters. So that's also possible, especially we see this quite a few of 5-meter chambers in Europe and Asia. So that all these requirements feed into our design considerations. We would come up with and also there are some guidelines, general guidelines of I call these rules of thumb that you need to observe for designing a chamber. So basically these rules of thumbs are a rough estimate of what the chamber roughly is going to look like. So all these things feed into the design. We would come up with the initial design. So that after that, then we go into a computer optimization process. So we would simulate that chamber. We go back and forth until we meet all the requirements, or if we can't do all the requirements within the limitation, then we say what kind of compromise you would like to make, and then we would enter into that discussion. So essentially we go into this loop until we acted out of it. We have a design, and then we want to obviously you would construct the chamber and measure it. So that's kind of the process. So I talked about the general rules of thumb in terms of general chamber designs. Just kind of want to lay out some of these rules of thumb and should be observed when sizing an EMC chamber once the quiet zone size and test distance are known. And so these are rules of thumbs. Many times you would violate it, or you don't have to observe them all the time. That's why you enter into a design process. But the general rules is that slant measurement axis is preferred so that reflections from the sidewalls do not enter in phase into the test area. So when you have a chamber design, we typically don't want to do the measurement right in the center of the chamber. So that's where it's likely to be a worse performance, because now the reflections will end up adding in phase. At some frequency, it's going to add up in phase and really kind of adding and subtracting, amplifying that adding and subtracting effect, so that your chamber doesn't perform very well. And also the separation distance between the antenna and the absorber tips should be larger than 1 meter to avoid excessive coupling between the absorber and the antenna. So this one is a rule that we oftentimes violate in our real designs, but this has to be something that you have to be able to simulate and then see what effect that can have. And also you need to remember for antenna mast, that's a misspelling, antenna tower mast, especially for these bore side towers, that the back side of the tower actually tilts up. So I don't know if you've seen some of these bore side towers. And then you need to make sure when you tilt up the back side of the tower, you've got enough height. So the antenna, the goal for that measurement is the antenna need to be able to scan from 1 to 4 meters in height. So the backside, when it tilts up, if you don't have enough height in the back, you can hit the wall, the ceilings. You can't really scan to 4 meters. That would be a problem. So a lot of these are geometry based. So, making sure that things fit in a chamber. So this is kind of the picture, a summary of that geometry based rules, that you need to make sure if you put a turntable, this is your quiet zone, you want to make sure this distance is greater than 1 meter. And then the side behind that is we would like the antenna, actually receive antenna, to be 1.5 meters behind the back wall, the front wall, or back front wall in this case. I call this side front wall. So you want to make sure that's 1.5 meters, and then the side is 1 meter. So like I said, this is what we like to have. This is kind of the starting point. You don't always get that in the actual design process because of the limitations of the chamber, limitations of the size of the room that we have to fit in. In terms of height, I kind of mentioned that this antenna needs to scan 1 to 4 meters in height. And you also have to remember when this antenna is 4 meters, and the EMC requirements is that the maximum antenna can be 1.5 meters in width. That means the tip of the absorber is actually at 4.75 meters. And then if you want to keep so that means really if this is 1 meter from the tip of the absorber, your tip of the antenna to the absorber is actually only 25 centimeters. So that's, a lot of times that's okay, but you also have to make sure that the chamber performance is not going to be negatively impacted by these compromises you're going to make. So just a quick review of what the NSA is. There is a lot of confusions about what this delta NSA is, because the standards talk about the theoretical NSA and comparison, etc. But in the end, we're actually working on a new standard in the C63 committees. There's going to be a new standard come out, C63.25.3, and that's going to include all the site validation requirements for below 1 gigahertz. So that's going to be moved out of C63.4. So we actually clarified quite a few things in the standards. So basically, when you talk about NSA, the theory kind of goes out the window, and what you're really looking at is a comparison of how this antenna performs in the chamber as opposed to how it performed in a large open area test site, because the theory is quite complicated. And then the theoretical NSA model that's used in the standards is based on the point dipole, and that has a lot of differences from the real antenna that you use for measurements. So that theory has a lot of inaccuracies or approximations in it. And so those inaccuracies actually cause a lot of problems in terms of comparison. And so that's why the CISPR standard actually goes to this other method called reference site method. So basically you measure the performance, the antenna response in the chamber, and you take it to a really good site, you compare the difference. That's essentially what's happening. So then what you're talking about is that basically the NSA requirement is this kind of a setup, and you measure the site attenuation between the pair of antennas. And the reason it's called normalized site attenuation is that you actually divide the antenna factors from the transmit antenna and the receive antenna out. So you take a division that's normalizing the both antenna factor out. So the thinking was that once you normalize the antenna factors out, this NSA number is going to be independent from antennas. But that's not what's happening in real life. The antennas can't be simply normalized just by the antenna factors. And there are a lot of antenna interactions and pattern effects that you can't normalize out. That's why the NSA requirements in the standards kind of go in the ways of site comparison method, or numerical method. Actually, the other method in the C63 standard is actually simulating real antennas, and then over the half space ideal situation, you can compare the performance to that. The other question that we get asked quite a bit is, why do we scan 1 to 4 meters in height? And this is because of this ground plane, because you know, when you have an antenna that's transmitting over a ground plane, when you receive the antennas, that these two rays, one coming from the antenna, one coming from the image below the ground, they sometimes, these two rays can add up in phase or out of phase. And so then you end up with this interference pattern. For example, the green line is 1 gigahertz. You can see the x-axis is the height of the antenna scan. So in this case, I drew a lot more than 1 to 4, but 1 to 4 meters is what you look at typically. And then the vertical axis is the response between two antennas. So you can see as antenna goes up and down, and you're going to experience a peak and valley depending on whether these two rays add or subtract in phase. What's interesting to notice is that at low frequency horizontal polarization, and you're pretty much getting the maximum response at 4 meter height. So that means you're scanning 1 to 4. The only useful data you're grabbing out of this NSA measurement is at the top of the tower, really, when you're doing this NSA measurements. But at different frequencies, of course, at lower frequency, horizontal 200 megahertz, you're grabbing the useful data. The maximum response is actually at the very bottom of the tower scan. And of course, at higher frequencies, and it becomes a lot more complicated. You experience multiple peaks and valleys. And typically at lower end is where your highest peak is. So typically when the chamber is failing at a lower frequency horizontal polarization, you probably should move your antenna to the top of the tower and look at that position. Probably that's where you're grabbing your data, actually doing the NSA measurement. So back to simulation, what is the real challenge in terms of trying to predict chamber performance? I kind of alluded to this fact earlier. Even though 100 megahertz is the most critical frequency, below 100 megahertz is the most critical frequency in terms of designing the chamber, especially figuring out the size of the absorbers, size of the chamber, etc. This is the most critical frequency range. If you are experienced with site validations, you would know that most chambers pass or fail in this frequency range below 200 megahertz. A lot of times below 100 megahertz. Even though this is very critical, we said the GO model is the most lacking in accuracy. So we got this problem we need to deal with. So in this presentation, I'm going to show you an improved algorithm for simulating EMC chambers. So what we do is kind of a three-step process. First, we treat the first antenna and the absorber interface in a more rigorous manner, what I call discrete complex image method. I'll explain that a little better in a few slides later. So this is we would treat the discrete image, treat that first interface more rigorously than the ray trace method. For the higher order reflections, where the reflections are farther away from the antenna, we can go back to our ray tracing, because we know the ray tracing is the limitation here is really about near field treatment. We're not treating the near field effects very well. But when you go farther away, the near field effects kind of dropping off, we can use higher order reflections using these ray tracing methods. So this hybrid approach is shown to be much more accurate, and it retains the efficiency of the GO model, yet it will improve the accuracy, especially below 100 megahertz. So like I said, this is a three-step process. First step is actually to change the absorber into a homogenized model. So at very low frequency, when you look at the incident wave hitting on the periodic structure, like an absorber structure, you can think of this as a layered material. So each layer would have a different material property. So when these periods are small, this is a very valid approximation when the period between the pyramids. So it's kind of like you have a eyesight that's not very, not a laser focus, laser 20/20 vision. Say your vision is kind of fuzzy. You look at something, you don't really see the pyramids, individual pyramids. What you see is kind of a structure that's kind of an average structure in each layer. So you can think of these layers. Each layer is, if I cut this into layers, first layer would have a mix of absorbers and air, And then the next layer would be more absorbers than air, and then etc. When you go to the very bottom, you can see pretty much all absorbers. And if I can figure out each layer what the effective material property is, and these two in terms of electromagnetics at these low frequencies behavior, they're equivalent. So this is called homogenization. Basically, you homogenize the absorber into a homogeneous model for each layer. And so how do we do that? We can apply a full wave simulation to get that information. Basically, what you do is you send a plane wave into a unit cell. So you can have this periodic structure. For example, we use HFSS, but you can use many other commercial or homebrew software package to do this. You have a periodic boundary conditions you set up, and then you send a plane wave into this periodic structure. And then what you do is you integrate, because by definition, for each layer, the mu times H that gives you the B field, and the B field over the H field would give you the effective permeability or permittivity. And so what you do is you integrate all these, say for each layer, you would integrate all the H field and also the material at each position. And then you take the integration over the integration of the field in that layer, you would get the effective material property for that layer. So this can be done very rigorously by full wave simulation. So then we will have a very good model of the absorbers in terms of this layered model. So how valid is that? And this is a comparison of showing the reflectivity of the absorber. So this is actual absorber that we use in the chamber. This is a 60 centimeter hybrid EMC absorbers. So you don't really see this is actually hollow. So the structure is not a pyramid, solid pyramid. There's actually air inside as well. And then there's a ferrite tile in the back. So we basically cut this absorber into 13 layers, and each layer we would find the equivalent material property. And what you're looking at on the right-hand side is the reflectivity of the absorber. Basically, what is the return loss if I send a plane wave? What is the reflected wave compared to the incident wave in dB? So this is a figure of merit for absorbers at 90-degree incident angle. So right on to the direct incident angle, right at the 90-degree angle. And so the lower this number is, the better the reflectivity is. It means the absorber absorbs more energy. So this is a figure of merit for absorbers. And you look at the full wave simulation, just simulating this real structure, and that gives you the cross. And then the homogenized model gave me the red curve. You can see they stay on top of each other. And many times people use this, the approximate rule is a Maxwell-Garnett rule. It's a mixing rule. Basically, is look at the volume occupation of the material and then do an average that way. So that's not a very good approximation. You can see that it has a lot bigger error doing these Maxwell-Garnett rule mixing. Since this step is a step we really don't need to take a lot of approximations, because we only do this for once per absorber, and we can do this very well in today's computer. So there's very little reason to try to approximate this step. So once we do that, we basically turn a chamber full of absorbers into a metal box with layered materials on top of it. And so that simplifies the simulation model. And then this below a couple hundred megahertz, below 500 megahertz, this is very, very accurate in this representation of the chamber. So the second step I mentioned earlier is the DCIM, Discrete Complex Image Method. So what is this? So once you have layered models, so this is your chamber wall, and then you have this layered model sitting on top of the chamber wall, and your antenna is sitting on top of this material. And so basically you have an antenna over a layered media problem to solve, right? This is what you're trying to solve electromagnetically. And the Green's function for that, for antenna over a layered media, or a point source over a layered media, that does exist, but it's still very computationally expensive to try to solve that rigorously. So this is where the complex image method comes in. it turns out that that same problem can be represented by an antenna on top and then a bunch of images on the bottom. So in normal, if it's a PEC ground plane, you know that the image theory says there is one on top and then there is one image below. But in this case, you're going to have one image, one original source and a bunch of images below. And then also to make the math work, I don't know why it's jumping again. I had this problem in another presentation I had earlier. And so that you can to make this math work, these images have to be located in a complex location, complex distance away from the interface. So obviously that's not physical. You can't have complex distances. You can't measure using a ruler to measure how far that is away, 1 plus 5j. That's not a physical location, but mathematically it works. So then, so this is basically you're turning this problem into an antenna and a bunch of images at complex distance away. So therefore, the moniker of discrete complex image method. So using this method and the wave above the interface is actually very rigorously solved. It's a very accurate solution. So one obvious problem with this complex image scheme is that because now the images are all at complex positions or virtual positions, like we're doing this meeting at, you can't really further bounce these images anymore, right? If you have a real image, you can bounce the image on different walls and trace this ray tracing these further images. But if it's a complex virtual thing, you don't know what to do with that. And fortunately, that these higher order reflections, now near field effects is very much attenuated, right? Because now you're farther away from interface, these near field effect is not a big deal anymore. And we can actually fall back to our traditional retracing method to deal with the higher order reflections. One is higher order reflection, meaning I bounce off this wall and then it bounce off of another wall in the chamber. So that's what this complex image, discrete complex image is about. And then the third step is that I already talked about this a little bit. Then we go for higher order reflections. We go to this traditional retracing method. So you can bounce these rays further in the other walls and other reflections. The benefit of using this hybrid approach is that obviously we're going to have a much better accuracy in terms of near field effects, especially at low frequencies. Now we're going to be able to deal with these low frequency near field effects much better than the traditional ray tracing method. So there was an earlier question that people asked that why couldn't you do the reflection? Could you treat this problem as you send a plane wave and then you treat this whole problem as a impedance interface, a thin impedance interface, and then you just look at the reflectivity of that surface, and then you can trace doing the ray trace that way. So that's actually exactly what we do in the traditional ray tracing method. The method with that is that you're assuming there is a plane wave coming in and there is a plane wave coming out. And that's why it's not accurate at lower frequencies. You don't necessarily have a plane wave situation. And also what you come out of this reflection is not a plane wave reflection. You have all kinds of surface waves and also the near field effects, and all that is not considered by that treatment. So that's why this DCIM approach is much more accurate. So I just kind of mentioned that. So we also, in terms of retracing, we also apply a visibility tree scheme, visibility tree scheme. I don't really need to get into the details, but the upshot of this is really, this allows us to simulate retracing in an arbitrarily shaped chamber. So traditional retracing also kind of limit, you have a rectangular box. And of course, you can be a lot more sophisticated, and so this visibility tree scheme is one of the methods that allows us to simulate chamber, arbitrarily shaped chamber. It doesn't have to be a rectangular box. So actually, I will show an example where we don't really need to simulate just a box kind of chamber. So how good is the simulation? This is a comparison So earlier I said the full wave simulation is not very feasible. It takes weeks to run for a full chamber simulation. But for this comparison purpose, we actually bit the bullet and actually did the full wave simulation for a small chamber. And this is the circle is the full HFSS full wave simulation result. We consider this as our reference because we think that's fairly accurate. And this is the horizontal polarization on the left and vertical polarization on the right. And this is a 3-meter chamber with hybrid absorbers. And it's kind of the arrangement of the setup. And our complex image retracing method, that this proposed hybrid approach is this red line. You can see our red line lines up with the simulation, with the full wave simulation very well. And actually measurement confirms that. The measurement actually lines up with both of them. And so this is the traditional ray tracing method, which is the green line. You can see at low frequency, we really have a problem in terms of accuracy. And this is, like I said, the chamber good or bad or pass or fail is likely to be determined in this frequency range. If we're not accurate in this frequency range, the tool, the usage of the tool is pretty limited. And then vertical polarization, we see the same thing. The low frequency, we're off by almost a dB in terms of prediction by using the traditional ray tracing, versus the complex image method gives us a lot more accurate results. And this is another comparison for different position. This actually, the chart should be left position is actually, it's the antenna position is actually closer to this left wall. And so you can see the same kind of trend, the same kind of behavior, that our complex image plus retracing hybrid method is very accurate in terms of comparing to the full wave simulation. So we established the accuracy of the method. The other thing is that it's really about the efficiency of the hybrid method. It's really accurate and also can simulate the chamber within a few minutes versus a week or more in terms of simulation. This is pretty enabling, allows us to do what if studies and different scenario studies and optimization studies. So that's a must. So when we build a chamber simulation tool, these are the things we must have. We must have accuracy. That goes without saying. If it's not accurate, then garbage in, garbage out. This is not very useful at all. And the second thing is this efficiency. And so it allows us to do these different type of studies. And also the flexibility to allow us to simulate various test scenarios, for example, delta NSA, free space NSA, psi VSWR for high frequencies, field uniformity for immunities measurements, and things like that. And the other thing that would be nice to have is a visualization of the rays in the chamber. If we can see how the waves can bounce in the chamber, this may give us some design ideas about where we can effectively place the absorbers and how we can arrange the shape of the chamber to make sure these bounces are not going directly back into the quiet zone and affect our testings. So then this is a very useful thing that if we have that would be a very useful tool, which is going to be shown on this slide here. So this is when we build the tool, this is one of the things we really we like to use. This is actually a psi VSWR measurement setup. You can see there's a floor patch absorbers. And what you're seeing on the screen is these blue lines are first bounces. First bounces being that the transmit antenna will go to a surface and bounce off one time and reach the other antenna. So these are super important. When it hits the wall, we want to make sure the absorber is really doing its job, is kind of eat up this energy at these first reflection points. So these what we call critical points. If you design a chamber, you want to make sure these areas are well covered with the best absorbers you can get. And the red dots here are shown as second bounces, meaning the antennas, the waves are going to bounce off wall and another wall twice, two walls before it end up at the receive antenna. So these are, also kind of important because we know, the waves are still consist of considerable energies with these two bounces. And you want to make sure your chambers are well covered in the two bounces. And also sometimes the high frequencies, when you have absorbers only ferrite tiles, these tiles are not very effective at high frequencies. And these two bounces, if two bounces are, one is off of a ferrite tile, is almost like bouncing off of a metal surface. You want to also make sure, these are well covered as well. So, with these kind of visualization, it can give you some ideas about how you can do chamber optimizations in terms of layout, absorber layouts. So you can do mixed coverages, and this tool would allow us to do simulations, allows us to put some absorbers in partial areas, and then the ray tracing would be flexible enough to understand that these walls are not consist of all one uniform type of absorbers. So you can do mixed absorber coverages on a single wall. So enough of the discussions about theory and what we do in terms of simulation. People, we want to see some real world examples and how these simulations aid us in designing some of these chambers. So the first case study is a very compact 3-meter chamber. So you can see this chamber, the turntable almost occupies the entire width of the chamber. So this is a very compact room. The size of the room is 8.6 meter long this way, and then width is 5.1 meters, and then the height is 5.8 meters. If you look at the geometries of where things fit, this thing barely fits, right? The tower is probably, the chamber is just tall enough to do a 1 to 4 meter scan, and the width and the antenna height and size wise, it's a tight fit. And then the absorbers in this room is 60 centimeter hybrid absorbers. So these absorbers are 60 centimeters tall, and you can see the ferrite tiles is lined everywhere in the room. But the foam absorber on top of the tiles is partially lined. Some areas do not get coverage for the whole hybrid absorbers. So this is a top view of the chamber, and you can see the quiet zone turntable is 2 meter in diameter. And the test I mentioned earlier, that you don't want to do this measurement right dead in the center. You typically want to have an offset, kind of break up the reflections. So this is the top view of the chamber, and this is a picture going from the other way. The earlier picture you see from this antenna's point of view. Now you're going back the other way from the receive antenna point of view, looking back, transmit antenna point of view, looking at the other wall. So this is the setup, and then this is the simulation results. The simulation result is on the right. So this is frequency from 30 megahertz to 200 megahertz. So the chamber is deemed good if it's within plus minus 4 dB, and you can see this chamber is well within 4 dB. So the legend and the notation here is H means it's horizontal polarization, and U means the transmit antenna, which is the antenna on the turntable side. You are required to measure at two heights, one at lower height, one at higher upper height. So this U means upper height. If this letter is L, means at the lower height. That's the transmit antenna height. And then the last number here is the antenna location on the turntable, transmit antenna. So L is left, and this number R is right, F front, center. So this is kind of the key. So this is basically what you're looking at is the horizontal polarization at 3 meter distance, the different NSAs at the different locations and different antenna height, transmit antenna heights. And you can see the simulation matches very well with our measured data, and the trend and everything matches up. We have a very good prediction of what the chamber looks like even before we constructed this chamber, and when the measurement bears that out. So the horizontal polarization, and this is the vertical polarization. You see a little more variations comparing the measurement and simulations. There are several reasons for that. One of the reasons is that the vertical measurement has a lot more impact from the environment. For example, the tower that's in the measurement, that the tower is actually polarized with the vertical polarization. Also the cable drape treatments and all those things come into measurement things that we don't necessarily model in our simulation. So you see a little bit more variation, but the overall comparison is still very good. And we can see the comparison, they do compare very favorably with the measurement and simulation. So that's a 3-meter chamber. And the challenge is that 3-meter chamber, a lot of near field effects. And we have shown the near field effects is adequately dealt with in the hybrid DCIM approach. So one of the things I mentioned earlier, you don't want to do the dead center line. And so this is just a thought experiment. I do, okay, what if I do that? So I didn't really do that in the measurement, but the simulation, I can easily do that. I can easily simulate the chamber with the antenna, read that in the axis, in the center axis. You can see the same chamber that passed very well earlier. And actually, it's a failing measurement in this arrangement. And you can see the NSA is exceeding 4 dB when I place the antenna like that. So this is the other thing we could optimize. It doesn't mean, you know, the angle there is not a magic angle here, 14 degrees, but you can, simulation wise, you can really play with this and see where the, you know, for this arrangement, what is the best angle. That before you even go into the measurement, instead of messing with it in the measurement, you can actually go in there, predetermine your angle by simulation. And that would save a lot of test time, because each measurement, it's easy to sit here and talk about measurements, but you know, each measurement takes quite a while. You sit there and wait for your results, and that's a tedious process that you can bypass with the simulation very quickly. So the other thought experiment is that the people like to do refurbishment of an old chamber. And so we've seen this done. This is not actually a thought experiment. This actually, people have done it. And they have a ferrite tile lined room, and they think, okay, I just go out and buy some microwave absorbers and tape them on the wall. I would have a chamber that can go up in above 1 gigahertz. I would get the best of both worlds, right? You have a chamber that can cover the low frequency, and then have absorbers to cover the higher frequency with these microwave absorbers. So things is not that easy. It turns out that's not a very good idea at all. And if you put microwave absorbers over ferrite tiles, that equals to trouble. And the reason for that is this: so the transmission line theory, we know we don't want to put a high impedance structure with a low impedance structure together. When you have a big mismatch in characteristic impedance in transmission line, we know we have a bad reflection. But for absorbers, the impedance for absorbers is, we know in the material, is square root of mu over epsilon. Mu is the permeability, epsilon is permittivity. So for absorbers, you know, there's no mu is relative mu is 1, but epsilon is high. So this is a low impedance material. And for ferrite tiles, it's just the opposite. You have a high mu and low epsilon. So the ferrite tile has high impedance. When you put these two together, you have a bad mismatch between the two. And then you're going to have some frequency range is very bad. You're going to have a very bad reflections. So this is what's happening on this right-hand chart. What you're looking at is the reflectivity of the absorber versus frequency. So the hybrid, the microwave absorber, of course, without ferrite tile, it doesn't perform very well. And you can see that this is the blue dashed line. The low frequency, it doesn't do much. And then before it gets into about 200 megahertz, it doesn't, you know, the reflectivity is pretty bad. It doesn't absorb much energy. And the ferrite tile actually works really well at low frequency. That's why you want to use these tiles for low frequency. But when you put these two together, you don't get the best of these two. What you get is actually sometimes is worse than both. And in some frequencies, it's actually pretty bad. And you know, even at the below 100 megahertz, the whole frequency range, you only get, you know, a couple of 6-7 dB range reflectivity, which is not nearly enough for a performing chamber. So this is not a good idea. Don't do that. So we spend a lot of effort and energy at in our company and probably other companies as well, to try to match this absorber, optimize the design, making sure the foam on top of the absorber work with the ferrite tiles. And they're tile and absorber specific too. So we actually do optimization processes and making sure the loading and everything, they're matching the shape and then the material property. So if you just slap these two things together, they don't work very well. Okay, so what if I really do that? And this is the NSA performance. If I do these, align this room with these kind of a microwave absorber on tile, and you can see this chamber performs horribly. And it's not even in the ballpark in terms of meeting plus minus 4 dB requirements. So don't be surprised if you do that. Same thing with immunity chambers. If you just put absorbers on top of the immunity chambers without consideration of a match, you're going to have a horrible immunity chamber as well. So case study number 2. So we talked that was a small chamber. So this is a larger 10-meter chamber. This chamber is quite a bit larger, and then the absorber is a 1.25 meter tall absorber. So they're a bigger absorber as well in a 10-meter chamber. And this is the picture of the chamber and top view. And this is actually the one you saw earlier. This is a dual range chamber, meaning they have 2 receive antenna range. So this chamber is a little wider than normal chambers because you have to accommodate 2 receive antennas in this room. Okay, so that's the top view of the chamber. So this is, again, the comparison. Left side is the measurement data, right side is the simulation data. And you can clearly see the correlation for the polarizations. A low frequency, this one is a little more variations because now you have another tower that in the simulation we really don't have the other structures, but in the in the real chamber we do. So, and then the vertical polarization. These slides are really just jumping by themselves. The second time I run into this for a presentation. So the vertical polarization, again, we have very good correlations between the measurement and simulation. The simulation, we predicted the performance of the chamber a little over 3 dB, so it's right there, measurement at 3 dB in the measurements. So the other chamber is a kind of a unique chamber. It's almost like a tampon in one of the books by Lee Hemming. So this is a semi-anechoic chamber, automotive chamber. Some of you guys might know what this is. So this is the actual chamber that has this design, very irregular shapes. The reason I want to show this is that we show these simulation tools can deal with these kind of design as well as rectangular boxes. So the quiet zone is 6 meter. And so this is the view of the existing design. Everything is to scale. So you can see this is in meter, top view, this is in meter. So if you don't need to adjust your eyesight, this absorber is indeed that big. There are 2.7 meter long, 9 feet long absorbers on these end walls. So the reason for that is this chamber was designed and built before the days of ferrite tiles. And so back then, the only way to get down to low frequency is use these exceedingly long absorbers to get down to low frequency. So there's no tile in this chamber. So on the side, obviously on the side walls and these areas, you can't afford to have these absorbers. You can see everything barely fits because of the absorbers are so large. And so this is a picture on the left side is showing the normal, the absorber performance thickness in wavelengths in terms of reflectivity versus the thickness of the absorber. So what you're looking at is the longer the absorber in wavelength, it's just jumping. The longer the absorber in wavelength, the better the reflectivity is in terms of the better the absorber can absorb energy. So to get this absorber to perform in like the 15 dB range, you really need the absorber to be 3/10 of a wavelength to be able to perform. So that's why these absorbers are so large. At 30 megahertz, the wavelength is 10 meters. So a third of the 3/10 of a wavelength, it would be 3 meters. So that's why these absorbers are almost 3 meters to get down, trying to get down the reflectivity to that low, to the acceptable performance range. And you can see if I do the simulation with our tool, you can see this chamber, even with that long absorbers, because the sidewalls are not very long, you don't have the space to do that. And this chamber at low frequencies by today's standards, is not that good. It exceeds the 4 dB in many different cases. So what if we change the absorber to a more modern absorber using the hybrid 1.25 meter tall ferrite and foam hybrid absorbers? And this is the arrangement. You can see now the absorbers are much smaller everywhere. And actually, you have a lot more space now. So if I do that, this chamber is going to perform like this. Actually look at the NSA performance from 30 to 200 megahertz is really outstanding if we do this. This chamber is less than 2 dB. For a chamber the size for the quiet zone of a 6 meter diameter, which is really big, this is really outstanding for this chamber. So this chart kind of give you some ideas why this absorber performs so well. Is that you can see the shape of the chamber does provide a lot of advantages, but by directing the reflections to other areas into the quiet, not into the quiet zone directly. So the other study is a high frequency chamber design. This is a failed VSWR site VSWR chamber performance. My colleague Anoop is online. Anoop and I did a video, 40-minute video on YouTube. It's published. We did this for the symposium last year, but it's published on YouTube. If you're interested in how you can debug a failing chamber, failed site VSWR, go look at that video. That has a lot more detail than what I covered today. But this one gives you a flavor of how a tool like this can help you debug a high frequency chamber as well. We talked about NSA was all low frequency. So obviously for site VSWR, you need to meet 6 dB. This chamber failed 6 dB. So how do we want to figure out what's wrong with this chamber? It turns out if we do time domain measurements, basically you take the S21, complex S21, you convert that into time domain, you can actually view the antenna response in time domain. This is through Fourier transform. So your measurement is still frequency domain. The time domain is just mathematically transformed into time domain. So when you do that, you would see a main response, that's the antenna to antenna response, and all the other later time, the x-axis is the time, y-axis is the dB in reflection. And you can see the later reflections are somewhere, these are the reflections off of the chamber, these other peaks. So obviously one of these peaks is going to contribute to or one or more of these peaks is going to contribute to the failing of this chamber. We want to figure out which one of these is the culprit. So through time domain method, we can figure out, say, like, let's look at this one here, and we know the difference in time between the main peak and the one that happens, the reflection happens. And then from the geometry, you can figure out this main peak is going to happen at, if this is the measurement antenna, they're 4.1 meters, and the reflection is going to happen somewhere later with a later time. You know the time, you can figure out how far away this reflection point is in the chamber. So with that information, we can go back to this ray tracing tool and figure out what is the possible reflection that can have this time. And it turns out there are two candidates in this chamber. One is bouncing off the wall and then to the floor and to the other antenna. And the other one is on the other side of the wall that has a couple of bounces into the ground and back sidewall into the other chamber. So you go back and figure out which one would be the one that causes the problem. It turns out this is the one that caused the problem because for this measurement, I actually intentionally sabotaged the chamber by taking out the absorbers over here. And of course, when I fix that, and I get a passing chamber, and you can do this very quickly to figure out what's wrong with this chamber. So if you're, like I said, for more information, go watch that video if this is a topic you're interested in. I'm not going to go into much detail than this because of the time constraints. So I covered a lot of ground today in terms of chamber design. Just want to give you a flavor of the design process and our thinking processes in terms of design a chamber or optimizing a chamber. We have provided an overview of the design and how accurate our simulation tool can, how an accurate simulation tool can aid a challenging design. In the real world designs, you rarely run into a standard design. So we rarely run, maybe 1 out of 5 maybe is the chamber with design size and shape looks like the one that we've done it before. A lot of times everything is customized because of different considerations in the chamber. So you don't want to take a guess on what the design needs to be. It's just too risky. And you really need a trustworthy simulation tool. So that's what this presentation is about, and how we can get a trustworthy simulation tool and what kind of technologies we use for that. So through the several case studies, we have documented the features and the accuracies of a hybrid full wave, DCIM full wave, and geometric approach. And through this approach, we demonstrated how a simulation in combination with measurement can aid in debugging a non-compliant chamber as well for the high frequency case. So with that, I concluded my talk, and I'm right at maybe an hour. Oh, perfect. Before I yield the floor, I'd like to acknowledge a couple of people with ETS Lindgren, a couple of my colleagues that contributed to the work, antenna simulation and chamber simulation. So I'm just presenting the results from my group, and they did a lot of the behind the scenes work.
Okay, thank you so much, Zen, for your presentation. Very interesting, and I learned a few new things here today that I hadn't really considered before. So Janet and I've been chatting a bit, and can you still hear me?
Yeah, I'm
losing some sound here, but anyway.
Good. Hopefully everyone can gain some knowledge here. Didn't waste your 1 hour time.
No, it's good. I didn't really realize that absorber weared out over a period of time, so that's a new thing. Who knew? So, and also before we move on to the drawing, our awards chairman Jim Woodyard, who I believe is still on with us this evening. Jim actually helped prepare this letter I'm about to read to you. Dear Dr. Zhong Chen, on behalf of the Southeastern Michigan IEEE EMC Society Chapter 8, I wish to express appreciation for your presentation to our chapter on July the 15th, 2021, entitled Optimizing EMC and RF Chamber Design and Performance. The chapter has recognized your professional commitment to the education of our members with a speaker award, which includes a donation in your name to the IEEE EMC Society President's Memorial Scholarship Fund. Your name, topic, and presentation and donation may be viewed at the chapter's speaker award list on our website, along with a complete list of speaker awards since 2012. And I'll be emailing you an electronic copy of the of this letter that I'm reading to you right now. I guess I forgot to turn my camera on. So here, I'll turn my camera back on. Anyway,
appreciate it.
Here's a letter, which I guess is invisible because of my crazy background here. If you want to also send the slides to me, I will put the slides and the video presentation together. And if you want to send me the link to the other YouTube video that you mentioned, and when you're ending slides, I can put those all together and send them out to all the registrants for today's meeting.
Okay.
Would that be good? Okay. So we have come up with Amazon gift cards as the prize for this evening, so you must be present to win. And I used the Google random number generator, so we're going to use these random numbers and then go through the roster, and we're going to give out 3 prizes. The first prize will be
Scott.
Yeah.
Real quick, is there no questions?
Oh yeah, sorry.
The speaker, just because I'm afraid that Zhong's going to nod off and forget.
Yeah, let's.
So maybe we should do that first, and then we'll do that.
That's a great idea, Janet.
Yeah, because you know what? With the gift cards, there is a quiz.
Oh, you're doing a quiz this time. Okay.
Well, you know, just on some simple mathematical formulas related to ray
Okay.
tracing.
Okay,
Yeah.
well, we can do that.
Okay, so let's do the questions so that people can get up to speed.
Okay, so if you have a question, unmute your mic because most of you are muted right now. Do
And
your
I'm
question.
just kidding. There's no quiz.
Darn, we did have one time.
I
So
know. I'll think of it next time.
Yeah, but it didn't go well. So
I
I didn't want to repeat.
I think I was on the line when you did that.
You might have
Funny.
been.
Yeah.
That didn't go well.
Okay.
So anyway, if you have a question, open your mic and ask your question.
Yeah, actually, I have a question. When you did the simulations, what did you assume for like a? Did you actually model the antennas themselves, or did you make an assumption about like a plane wave? I'm kind of curious as to.
Yeah, yeah, good question. So it depends on the frequency. Lower frequency, the antennas you use for EMC measurements typically are pretty close to a dipole. You use biconical antennas mostly. But the simulation package, our tool has the capability of doing a couple of things. One is incorporate the antenna pattern into the ray tracing. So if you can incorporate, you can still consider your antenna as a point source, but you can incorporate the antenna radiation pattern into the simulation. So that's one way to do it. The other thing you could do is if you can represent your antenna as an array of some small point sources, you can put that into in the simulation. You could do it that way as well. But the simplest way, in terms of higher frequency, especially the antenna pattern comes in, and that model with incorporating the antenna pattern, for example, in our site VSWR method, we definitely need to model the antenna pattern because that has a significant impact on the performance of the chamber. So then that's the way we incorporate those in the simulation.
Okay, yeah, because as you probably as everybody well knows, there's like different types of antennas are used for different, in different sites for their measurements or whatever, and their antennas are really not like point sources. You have to look at their radiation patterns. Right. If you're in the far field, especially, to be able to understand what's going to happen.
Yeah. Right. So the low frequency one, actually, the point dipole model isn't very bad at all in terms of you can see the comparison that bears that out. Your antenna is pretty much a biconical antenna is a dipole antenna, but a higher frequency, definitely the antenna pattern comes into play significantly. We all know for site VSWR measurements, people have used different antennas. If they have a failing chamber, sometimes people switch out the antennas on the receive antenna side, for example, different receive antennas in the chamber, which is allowed. Actually, the standards recognize that, and they say if you qualify a chamber using a specific antenna as a receive antenna to qualify your site VSWR, you actually have to use that same type of antenna in the real measurement. So the qualification is only good for that type of antenna.
Okay, because I know like in a lot of cases too, if anything, everybody wants to use big wideband antennas like bicanalogs and all that because they can cover a wide frequency range. But the radiation pattern certainly changes as you go up in frequency. Right. It changes from, like you said, kind of like looking like a dipole, and now all of a sudden having more directivity, especially.
Yeah.
So it makes things interesting.
Yes.
Okay. Next question. Did anyone have another question? If so, unmute your mic.
So if you don't want to talk, you want to type, I can see your question as well. If you want to type in the question, that works for me as well.
Well, maybe we should move along. And after we're done with the drawing, if someone still wants to ask a question, that's fine too. So let's get going. So we have 3 Amazon gift cards this evening, courtesy of ETS Lindgren. The first one is for $75. The second will be for $50, and the third will be for $25.
Scott, you got to go the other way around. We got to build up
Okay.
the excitement for the 75 to
Okay.
be last.
Okay, that's a great idea. So the first one will be for the $25.
Yep.
And the first random number is 66. And the 66th person on our roster is Gregory McCormick. Greg, are you on the line?
I didn't see him.
I didn't see him. So I'll cross that one off. The next one is 117. 117 is Jeffrey Z, XIE. I didn't see him on there, so we'll cross out. Third one is number 91. 91 is Jamal Shafi.
Chapter chair from Rockford.
And again, not here.
Not here? Oh.
No.
Great
Next.
for an EMC chapter chair to get it.
Number 28. 28 is David Evans. Dave? Dave,
Okay.
unmute your mic. I think Dave, I saw his name anyway. Dave, you still here?
Yeah. He's waving down there.
Oh, okay, great. I have speaker view, so let me switch to a different view because I cannot see him. Oh, there you are. Hi, Dave.
Oh,
Congratulations. So Dave, you're gonna be getting a $25 Amazon card in the email somehow when we figure that out. Okay, congratulations. The next one is number 11. Number 11 is Sebastian Braun. I did not see him. Sebastian, are you here? I didn't think so. Number 2, Anoop. It was ETS though. Is that, should we not qualify that one?
Oh, I guess so. Sorry, Anoop.
Sorry, Anoop. Next lucky number was
the
84.
first time I won and I'm not eligible.
I know.
You'll have to quit your job, then we can send it to you. How's that? Next one is number 84 is Andre Plakhick in Russia. Andre, are you on the line? No.
Mm.
Next lucky number is 33. 33 is Richard Georgian.
Oh, Richard Durgarian.
Yeah, Georgian. He is not, I didn't see his name though. I did not.
He's a society photographer at the symposium.
Well,
is he on the line?
I don't think so.
Oh.
I didn't tally him. Next is number 50. Michael Kirkhart. Mike, you still here?
He asked the big question.
I know he did.
Oh, wow, yeah, the loudmouth is here.
The antenna guy.
Okay, Mike, you just won $25 gift card.
Awesome.
$50 gift card.
Yeah.
$50 gift card.
Oh, even better.
Yeah, $50. Congratulations, Michael. I'm running out of lucky numbers on my list here. Number 76. 76 is for, and Janet will have to do a drum roll if we finally get somebody. Number 76 for the grand prize, if he's here, and I did see his name earlier, for $75 is Kenji Naoi. Kenji, are you still here? Kenji, open your mic if you're still with us. He was here.
Don't see him.
He's gone. Okay, well.
Yeah, it's getting so exciting.
Dang. 56.
I think next time it's just one gift card.
Yeah, it takes too long. 56, Cindy Lee from Tesla. Cindy, are you still on the line? Yeah, I see her name here. Cindy, open
Yeah,
your
her
mic.
name shows up in the participant list. She's muted.
Yeah, Cindy, can you unmute? Cindy Lee.
Here, but she isn't here.
She's here, but she's not here. What do we
Maybe
do,
she's-
Janet?
Well, I think we give it to her because she's
Okay.
probably making dinner.
Okay. Well, it's your money, Janet, so that's fine. So Janet got Janet I said
Well, it's not my money, it's ETS Lindgren's money.
Oh, okay. Okay.
They're
so
the
that's-
sponsor.
So there's a question from Candace that's
Okay.
on the presentation. Is this similar to the method where you model the reflections by putting antennas in the model for the reflection, attenuated by the absorber? Trying to understand the question where you model the reflections by putting antennas in the model for the reflection. Yeah, Candace, maybe you can elaborate on the question. I'm not exactly sure I understand.
Okay, in the past, I've modeled taking the boundaries out. And then I just put the antennas in and you put them in the location that you would have them because of the reflection. And then you can just attenuate it.
Oh, okay. So you're talking about model the antenna in free space and then?
Well, so, you know, if you have a box and you have two antennas, so you have actually an infinite number of antenna reflections, right?
Right.
So you just model like the first 5 or something. And
Okay.
you can attenuate them.
Yeah, so that's a good, yeah, okay, I got it. So that's what traditionally, actually, see, I got these backup slides. So traditionally, when you do a ray tracing simulation, you have a center box. I call this a stacked matchbox method, stacked box method. So you have this is your chamber, then you just stack all these images, stack all these image chambers around it. And then what you do is you're saying, okay, the transmit one antenna, you transmit from here, and then you receive from there. And then you can have these images for these receivers at all these infinite numbers. As you go out, you can have infinite number of these things. And then you basically say, okay, the effective received power of this antenna is really the summation of this one and all the images of these summations. So that's the traditional ray tracing method. And the way you deal with the absorbers with this is that every time you go through a wall, you would go through some attenuations because that wall represents a reflection off of that wall. And then you would treat these absorbers as lossy transmissions, basically. And then if you simulate in the traditional way in the unit cell model, you would in the unit cell model you would calculate the reflection coefficient for each wall, and then you would multiply this ray by each reflection coefficients. Of course, it's a little more complicated than that because you have parallel and perpendicular waves, different polarizations. You have to treat them differently. And also different angles. So if you establish the lossiness of each at different angles and different polarizations, you can sum this. So that's the way you typically deal with tradition. But that's the problem with this method is that the near field effect is not effectively treated for especially the low frequency. That's kind of my discussions earlier, and how this method could be improved by using this hybrid approach. So yes, you can treat it that way as a first order approximation. At higher frequencies, they do work very well. So that's kind of the way you simulate these reflections in a chamber. So the other thing I didn't mention, I kind of mentioned in passing, is that we allow our method is that we allow the tracing rays in a more complicated manner, that we don't have to have these boxes stacked, because when you have a chamber that's irregular shaped, you can't stack these boxes anymore. So that's our visibility tree scheme. So but I don't really need to get into this unless you're really interested. You can read some references papers I can send you. If you send me an email, I can send you some of the publications we did, how to deal with that. The complication for the irregular shaped chamber is how to find these rays because you can send rays all over the place, then they may be useless rays. We never end up at the receiver position. So for example, you send that direction, it just bounces off, bounces all over the place, we'll never reach this antenna. That wouldn't be a useful ray for us. So then the only useful rays are the ones that can reach from one antenna to the other through these bounces. So that's kind of the challenge with the non-rectangular chamber ray tracing. It's a little more sophisticated than these stacked boxes. Does that answer your question?
Yeah, because I know that when I've done it in the past, I had to write the software. So it is different.
Yeah. So yeah, the other thing is if the antenna pattern, I don't know if that's what you're implying. The antenna pattern, you can definitely treat it. Think of this as you can have an antenna pattern, then your rays is going to be attenuated by the antenna pattern as well. So definitely that can be dealt with this retracing scheme.
Thank you.
Yeah.
Okay, any more questions?
Yeah, I have to ask this one. I'm not sure what the answer is, but I'm still trying to wrap my head around this complex distance thing that you brought up, as far as how you modeled the absorber.
Yeah.
And then trying to relate that to something physically, or am I just like, don't bother, it doesn't work?
Okay, let me take a crack at that. See if I can explain this in a more physical sense. So these materials, they have lossiness, so they're complex materials.
Right.
And the way that you can think of a reflection about, because what you're interested in is, say, if I have a point source here, I'm interested in the way the field over here.
Mm-hmm.
So you can think of the wave as an infinite sum of e to the j minus beta r. And right, because that's just a wave from different directions, from different distances. But sometimes in the near field, you have these evanescent mode. So the j can become the j beta r can become real, right? The beta doesn't have to be a real number. That number can be complex. So that's why to account for that complex behavior, you have to make R complex to make R complex to make that equation work. So your wave is still a sum of e to the minus j beta something, right? As a summation of these waves. So that's how you approximate the Green's function of a complex environment like that.
Okay, so here's my takeaway from this. Is what's going on. Yeah, you're right. These materials, the permittivity can become complex, but what that complex distance really is you still have the distance, but it's also accounting for the phase shift of of the wave coming off, right?
Yeah. Yeah. So also, even when the material is not complex, you have these evanescent modes. So the e to the j beta can be it's not a propagating wave, so it could be a real number there as well, instead of a imaginary number, right? Imaginary, if j beta r, that's an imaginary, then it's a propagating wave. If that number is not, then it's an evanescent wave. It's going to die off exponentially as you go away.
Okay.
So then even with a non-complex material, you could have these near field effects that's not taken care of by the plane wave approximation. And
Yes, you're right. You're right. You're right.
Yeah. Yeah.
I'm just thinking back. You got me thinking back to the actual full field equations for like a Hertzian dipole, and I'm like, yeah, okay.
Yeah, so it does take care of also the material property, actually, like you said, the material is complex, and that behavior is very complex as well. So that you basically try to approximate that spatial Green's function into, try to fit that into a series sum, and that series sum end up being you have complex distances.
Okay, yeah, I think that helps a lot now. But you just first when you mentioned complex distance, it's like, my mind went poof,
It's not
but then
very
it's like, well, wait a minute here.
Yeah, I know. I had the same struggle. It's like, well, how do I explain this complex depth?
But it sounds cool.
Yeah.
Okay, thanks.
Yeah, no problem.
Okay. Any more questions for Zhong?
Dear Mr. Zhang, very good presentation. Is there any proposed measurement time regarding to radiation reflections, especially in first and second bounces?
Is there any? I'm sorry, I didn't.
Any proposed measurement time?
Oh, measurement time.
Measurement, yeah.
Comparison in terms of simulation time or measurement time? What?
Both, actually. I mean measurement time because of the first and second bounces.
Because in measurement, you don't really see the bounces. You just take a measurement. So the bounces are really a conceptual way for simulation. In terms of simulation time, these things can run very fast. I kind of mentioned that. So when you have an NSA testing, you have I don't know how many, 8. It's like you got 8 geometries, different polarization. I think 40 setups. So that whole thing can take a couple of minutes to simulate using this complex image and ray tracing method. So I can basically simulate the whole chamber, all the different test scenarios in a couple of minutes, versus a real full wave simulation. We're talking about weeks. So that's the efficiency that this method gives. It's a little slower than ray tracing, but not much. Even ray tracing takes a minute or two. So this thing adds about it's maybe 30% of time into my simulation, possibly. I'm not exactly sure. I never timed this, but it's fast enough that it's really practical for us to do simulations. But in terms of the question about measurement time, I'm not sure what that means. Maybe you can elaborate on that, or if you, yeah, I'm just not sure what the question is.
I mean, the time takes long for reflecting the waves from evanescent waves and in measurements. I mean that.
So how many times do I need to bounce this before the wave is considered not large enough anymore? Is that the question?
Yeah.
Okay. Yeah, a very good question. Actually, our software has a convergence check. So typically when the energy dies, it's kind of like your FDTD simulation. You look at the energy. If the energy dies to a certain level, you no longer need to consider it anymore. Or you can predetermine and say, okay, my experience tells me if I bounce 4 or 5 times, this is the wave's pretty much dead. So that's basically our approach. My experience is that a couple of 4 or 5 times is all it really takes, because we're talking about a lossy environment. If the absorber is a semi-decent, couple of 5 bounces, it probably is enough for the solutions to converge. But you can try it numerically, try more bounces, see if the results changes. If it doesn't change anymore, you're pretty much converged. But our software can deal with that as well to look at the energy level for convergence. Obviously, if you're dealing with a high Q environment, like almost like a reverb chamber, then this thing can bounce forever, never die. The only way for it to die is the propagation distance, but that takes forever.
Thank you so much. Thank you
Yeah,
so much.
no problem. Yeah.
Okay, any more questions for Zhong? Not hearing any, I'll turn the floor back to Janet O'Neill.
Thank you, Scott. We didn't have a chance to get into the midfield measurements, but we'll talk about that at the next chapter meeting perhaps. But anyway, I just wanted to thank everybody for allowing us to participate in your chapter meeting. It's been a pleasure working with you guys, and some of you might know that Scott and I go back, oh gosh, maybe even 30 years working on EMC chapter meetings and events, and we worked together on, I think, the first chapter tabletop show in Southeastern Michigan with
Yeah.
Clayton Paul years ago. So
Years
that's how
ago.
far back we go back. And now Scott is retiring, so our time together is coming to an end. So Scott, it's been a pleasure working with you, and I think everybody in the chapter will appreciate how much time and effort that you put into running these
thank you,
successful chapter meetings over the years. So thank you so much,
So-
and good luck on your tabletop show next month.
Thank you. To be clear,
That's
I'm
really
not
exciting.
retiring. I'm retiring from Yazaki, not from IEEE. I'm still planning on doing IEEE. So
Well, that's good, because we
So
don't
no-
want you to retire
don't
from
panic.
your real job, which
my real job, yeah, my
which
real
is
job.
EMC Society. You're a smart guy, Scott.
You're not gonna let him go. No way.
Oh, well, thank you, Kimball.
And thanks,
Um,
Zhong, for taking your time to share that presentation with us again, too.
Oh, my pleasure.
So as Janet mentioned, we're having our IEEE EMC Fest, our annual event, September the 30th. So please go to our website, emcfest.org, and you can register there. We already have a lot of the vendor tables almost sold out. And we have 3 very good speakers, all of them actually from Michigan this time. So I think that's going to be really nice. So I hope to see everybody on September the 30th this year at EMC Fest. So before you forget, go out and register, because you don't want to wait too long, because then the price goes up a bit. So we do have a discounted price for IEEE members, and it's just a little bit more if you're not a member. And it's a little bit less if you're retired. So go have a look at that, or if you're also a student. Okay, anything from anybody else before we stop this recording? Okay, I'm going to stop the recording. If people want to hang around, then